Hey, what's up, guys? This is Cheng here. So today, let's take a look at this number 480, sliding window median hard problem. Okay, so median is the middle value in an ordered integer list. If the size of the list is even, then there's no middle value. Basically, um, if the number of the size is odd, it's the odd number, then the median is the middle one. But if it's the number is even, then the middle is the middle two numbers divided by two. Okay, and then okay, given this definition of the median, and then you're given like an array of numbers, and there's a sliding window of size k, which is moving from the left to the right. Basically, there's a sliding window of size k, and it asks you to calculate uh, each median value of each the sliding window. Basically, while the sliding window is moved, every time when it reaches a new location, it asks you to calculate the median, and in the end, you need to return all the median numbers from left to right. Okay, so um, I think the description is pretty clear, and so I think the brute force way, right? I believe everyone should have already realized that basically we just need to maintain like this like array of the sliding window, and every time when we have a new sliding windows arrays, we just sort it, right? We sort the sliding window, and then we use the binary search to find not okay actually we sorry not binary search. We just find the middle one, or the middle two numbers. Okay, then we simply return the value. Basically, that's the brute force way, right? And cool. Let me try to implement that real quick to give us a starting point. Okay, basically, um, all we need to do is we just need to maintain like a sliding window here. Okay, and also, so when we maintain the sliding windows, right, we can just remove the last the last number, right? And then we added the front number so that we can maintain like the size of k. Okay. So the way I'm doing it, I'm just going to define like a current array here. Okay. And then so at the beginning, I'm just giving it like the k minus one. Okay. And then we have answer here. So basically from I in range like k minus 1 to n, right? Because the reason I'm doing this k minus 1 is I'm only initialize two numbers here, so that so basically we start from here. We start from k minus 1, and then we loop through until the last one. And here, so and if if the I is greater than k minus 1, right? Basically, if the k is greater than the length of the uh, if the length is greater than k, then we simply do a pop, right? We pop the first element by doing the pop 0, okay? And then after that, we add that, right? We add the current array with the latest number here. So basically here we're trying to like renew, basically to update the sliding window array, okay? So now we have a updated sliding window. We can simply like trying to get the median, right? So what's the median? Basically, we have two options, right? If the k is even, okay? Sorry, so here is odd. If it's odd one, then we know actually. So now we need to do a sorted, okay? sorted array equals to a sorted cardinal array, okay? And then the answer is simply the append sorted array k divided by 2, okay? Else if it's even, right? If it's an even one, we need to get two numbers, okay? So what's the two numbers? It's the k divided by 2 and what? So this 2 here. And sorted array k divided by 2 minus 1, okay? And then we need to divide it by 2. So yeah, it's pretty straightforward, right? Let's say we have 1, 2, 3, 4, okay? So the k is equal to 4, okay? And when we do the divided by 2, we have 2 here. The index 2, which is pointing to 3 here. So that we need to find the ones on the left for the other part of the median, right? And then in the end, we just divide it by 2, okay? And then we simply return, right? I think this should just work. Yeah, submit. Cool. At least it accepted, but as you guys can see here, it's not that fast. It only beats like 11%. So why is that? It's because of the time complexity here. Basically, as you guys can see, for the outer loop, we have we have an n here, right? How about the inner loop? So for the inner loop, we always sort the current array. So which is the k times log k. That's basically uh, the time complexity for the first. You can call it brute force solutions. Basically, we just maintain like a sliding window, and every time we just sort the sliding window, and then we just get the median directly. That's why we have a n times k times log k, because sorting is a k log k, and then on top of that we have an n here. That's why it's kind of slow. And I mean, if it's like just like this solutions here, probably this is not, shouldn't be marked as a hard problem. It will be like more like a medium or even an easy one, maybe. Okay. So what's make this one the hard problem is the second solution, where if we want to improve this, okay, basically the problem for now, right now is the how can we effectively find those two medium numbers or one medium number, okay. Um, Obviously, sorting is not that efficient. So what's the other way? Basically, we can use like a two priority queue to store those two numbers. Okay, why is that? Because if we split, I'm just using like this even sliding window size as an example because this is easier to help us understand the two priority solutions. Basically, if we split uh, this array, let's say if we have minus 1, 1, 2, 3, 4, and 5. So if we split this array into two parts, so the median number for this one is basically is the last character, is the last number of the first part subarray and the first number of the second part. Okay, and notice that they are like all sorted, and this part is also sorted. And since we don't care about all the other parts, all we care is basically we care about the biggest number, right, of the first part and the smallest number of the second part. So that's why we can use two priority queues, basically to maintain the biggest number of the first part and the second part, and the smallest number of the second part. Okay. Since in Python, the priority queue is like a mini heap. So that will just work by its nature for the second part. But for the first part, how can we maintain like the max number in the mini heap? We just need to, when we store the number, we just need to convert it to a negative value so that we can maintain the max number. I mean respectfully. Okay, and that's that. And then the next thing is that when we maintain those two priority queues, we have to make them balance, right? Well, so why is that? Because and mm, it's because when we insert, right? When we insert the sorry, okay. So why is that? Because when we try to do the insert, okay, will be insert based on the current medium value. Okay, so if the number we're inserting is greater than the current medium values, then we'll be inserting that value into the second part. If that value is smaller than the first is smaller than the medium value, and then we will insert into the first part. But if we're only doing that and we're not if we are not balanced those two arrays there, it's possible that because the way we're getting the medium is we're always getting the biggest number from the first part and the smallest number from the third part. If we're not going to balance these two parts here, it will be, let's say we have a 6 and 7s here later on, it will always basically append or always be inserting into the one part. In this case, it's the second part. So in that case, the second part will just keep increasing and increasing, and basically it's not balanced, which means the median value will be wrong. So basically, while inserting the numbers into those two subarray based on the current median, after that we also need to check the current length of the two parts. If they are not balanced, then we need to move one values either from this one to the other one, or from the left one to the right one. And the threshold for that is that we cannot, if any one of them, I mean basically if the right one is of the left one, the difference is greater than one, then we'll be uh, basically uh, balance those two arrays. And yeah, basically that's the basic idea of how we can maintain those two parts, right? Two subarray of the median, so that every time, I mean, we just need to either insert or also we need to remove. Basically, once one number has been moved outside of the sliding window, we also need to remove that number from either one of the two arrays, right? Based on the value. Mm, okay, I think that's basic idea here. And of course, we also need to take care of the uh, the even size sliding window and the odd size sliding window, or the even size sliding window. And so the way we are doing that is we are always storing so basically if the medium if the size is odd, we're always storing one more letter and one more numbers on the right side, which is the mini queue here, the mini priority queue here, so that, I mean, it's easier for us to calculate the median, because whenever the left side and right side are different, the length is different, we can always like get the value from the mini priority queue, which will be the medium at that moment. Okay, cool. So with that being said, let's try to code these things up. I'm going to comment out here, and let's see. Cool. So for this one, I mean, we're gonna be implementing a few helper functions, but to make this one more clear, I'll be implementing the main logic first. Basically, we have a minimum priority queue, okay, this one, and the maximum priority queue, okay. So for the minimum priority queue, okay, let me draw this. So for the minimum priority queue, the values we're saving here is here, okay, 1, 2, 3, 4, 5, 6, okay, and this is the max queue, priority queue. And this is the minimum priority queue. Okay, basically because the priority queue can only guarantee that the first element is the minimum one. Okay, that's why the minimum queue basically restoring the right part of the sliding window, of the sorted sliding window, and the max queue stores the left part. Okay, okay, and then basically in the minimum queue, right? So the something, it will be storing something like this, like 4, 5, and 6, or it could be 4, 6, 5, right? I mean in the priority queue, only the first one is guaranteed. The rest is not guaranteed. We only guarantee the first one is the smallest one. Okay. So here actually it's like the first one is minus 3, right? Minus 3, minus 1, or minus 2. Okay, because in order to keep the first one the biggest, right? In the mini queue here, we have to convert all of the members into the negative value. Okay, so so we have an n here equals to length of the numbers, right? Nums. Okay, and then we have an answer here. Okay, cool. So now let's try to loop through the numbers here. Okay, so the first one is we always insert. Okay, so we always insert the nums I here. Okay, that's how we do the insert. We always insert the current one, and then when the I is equal or greater than k, okay, which means that, let's say the k is equals to 3 here, right? So when I is 3, it means here. Okay, so when we are at this moment, we know that, okay, we need to remove, so from this one onward, every time we need to start removing the leftmost one out of the sliding window. Okay, that's why I'm going to remove the nums, which number, I minus k. Okay, so I'll be implementing the insert and remove later on. I'm just implementing the main logic here. Okay, so that's that. And so at this moment, right, so we're having like updated, same as this one, we are having a like updated uh, sliding window, or we have updated mini queue and the priority queue. Sorry, the mini queue and the max queue here. Now we can simply uh, get the median, but we only want to get the median when I is equal or greater than k minus 1. Okay, which means we only start getting the median from this position here. That's the k minus 1. Okay, and then we have answers append get medium. Okay, cool. So and then we just return. Okay, right. So basically that's the main idea here. Okay, and now let's implement those three helper functions here. So the first one is insert. Actually, you know what? Actually, the first one should be get medium because we'll be using the get medium in many places. Okay, so what get medium does is, assuming we have a updated mini queue and the maximum queue, we just need to get the medium out of from both of the mini queue and updated queue. Uh, mm, Basically, if the length, if the like I said, if the length of the mini queue is not the same as the length of the max queue, priority queue, okay? So we simply return the mini priority queue 0. So this is for the out case. For the out case, basically, for this case, in this case, the mini queue, okay, the mini queue will have 3 and 4, and the max queue will only have like -2 in this case. So in this case, we don't need to care about the maximum one because we know the mini queue, the first element in the mini queue will be our medium value here. Okay, and yeah, so I mean to do a sanity check here, because since we're doing this like in index here, we need to make sure there's a value inside that. Otherwise, we'll simply return 0 because we're getting this uh, okay, because when we do the insert, right, like I said, when we do both the insert and the remove, both of those helper functions will be using this get medium. So which means even at the first time, right, when both the mini queue and the max queue they are both 0, we'll still be trying to get we're still trying to get the medium at that moment. So that in that case, the max priority queue, and then we simply return 0. Otherwise, when we reach here, or or when we reach here, okay, we'll get a index does not exist exception. Okay, so back to our main logic here. So this is for out. Okay, out size. Okay, and this is like the even the even size. Okay, so when it's even size, what do? We get the value from both. Uh, but remember, since the value we're storing in the max priority queue is the negative, or it's a converted, right, converted value. When we're trying to get the value, we also need to convert it back. So which means we're gonna have like mini priority queue dot 0. Here is not a plus, it should be minus max priority queue 0, and then same thing, we also need to divide them by 2. Okay, cool. So that's the definition of the get medium. Okay, and now let's implement the insert. Okay, insert. So we insert a number here. So first thing first, let's get the medium, right? So both when we do the insert, either do the insert or delete, we always need to get the medium first. Medium, get medium. Okay, and Okay, cool. So here, if the number is smaller, it's smaller than the medium. Uh, uh, let let's do this. If the number is equal or greater than the medium, okay? So like I said, we are trying to maintain. Uh, so in the case of the odd sliding window size, we're trying to maintain the medium one with basically one more number in the mini queue here. That's why when we do the we're gonna implement when the number is equal, we're gonna insert it into the mini queue. Okay. Mm, let's see here. Does this one really matter? But let me see here. Okay. Okay, let me finish implementing this. Basically, if the number is equal or greater than the medium, right? We're storing that number onto the mini queue here. Basically, the way we're doing it, we're gonna do a heap queue dot heap push, okay, and we're gonna mini priority queue and num, okay, because on the mini queue we're storing the original value, okay. Else what? Else we push it to the other half, which is the max queue here. But when we do the push to the max priority queue, we need to convert it to its negative value. Okay. Okay. And then after inserting or remove, we need to balance the priority queue. Okay. So I'm going to create another helper function. It's called balance priority queue. Okay. And okay. So how are we going to balance that, right? I mean, like I said, if since we're always trying to make sure the minimum queue is always equal or greater than the max queue, okay, so that when we get the median, when it's outside, we can always only get the median from the mini size, so that when we do the balance, we have two steps here. The first one is if the length of the max priority queue is greater than the minimum priority queue. Okay, so in this case, we always try to move one item from the max priority queue to the minimum one. So how do we move it? Basically, we're moving the first one. Basically, we heap pop the basically the biggest the the first number from the max queue, and then we push it back into the mini queue. Uh, heap queue dot heap push. Okay, and mini priority queue, right? And the value we're getting here is that, remember, we're always every time we do a push to the mini queue, yeah, to the mini queue, right? Because we are getting the value from the max queue, okay, max priority queue, and the value is negative here, so that's why we also need to convert it back, okay. So that's when we need to the move element from the max queue to the mini queue. How about from mini queue to max queue, right? Since one difference, if mini queue has one more element than the max queue, we are fine. We don't want to move it because we want to make sure the mini queue will always has like equal or one more element than the max queue, so that when the only time when we need to move from minimum to max queue is the difference is greater than 2, which means if the mini priority queue minus length of the max priority queue is greater than 1, okay, then we need to move. Basically, we just need to do an opposite move from here. We need to move into the max queue, okay. Same thing here from the mini queue. That's how we do the balance, okay. So which means every time when we have an insert, we do a balance. Now the now the remove, okay. Also remove the number. Same thing here. We also need to get the medium number first. Medium, okay. And if basically we need to follow the same logic here because that's we need when we follow the same logic, then we can find out which priority queue we need to move it from. Basically, if this one, and then we need to move from the mini queue here, right? So that's the number. Otherwise, we move from the max queue. Okay. And again, after removal, we also need to balance the queue, the priority queue. Cool. Okay, I think that's it. Let's try to run the code here. In range. X not in uh, remove. Oh, sorry. When we move from the max queue, we need to do a minus one. Oh, and also one more thing is that, since we're going to do the remove here, right? And the thing for this remove part is the after removing, it's not guaranteeing that the remaining one is still like a heap, okay? Because the heap queue does not uh, give us like a remove method, and so that we only like use the standard like list remove functions. So basically, after this removal, we also need to make sure the heap is still the priority queue is still like maintained. So that's when we need to do a heapify here, minimum priority queue, and same thing here, the max queue. Yeah. Okay, this one accepted. Let's try to submit the code. Yeah, cool. So see, this one is faster. At least I think there are like more the faster ways here, maybe by using the tree set in the Java. But since I'm using Python here, the only option I have here, or at least I know, is by using like the priority queue. So what's the time complexity now? Uh, Still first one is still n, right? How about insert? What's the time complexity for insert? The get medium this is O1, right? So because when we get the medium, we only get one letters. So the first at most two numbers from the starting of the priority queue, which is O1. So this get media is O1. So the remaining left is like this is a log n, sorry, log k. Mm, yeah, it's a log k here because the heap push is a log k. So that's the insert. The issue is, I think the problem is not a problem. I think the difference is when we do the remove here. Uh, let's see. So I think you know, this part, remove and heapify, this part is like, it's not ideal, right? Because I think heapify takes like k log k time, something like this, right? Basically, when you try to remove an item from the sliding window, right? Or if you try to remove an item from the priority queue in Python, since Python itself it does not have like um, this built-in like remove method for the heap queue. So here ideally it should take it will take a k time k time. So basically, instead of n log k, it should be nk in this case. But the issue here is that I use the remove and the heapify here. So I believe this one is more than nk, but I haven't figured out a better way of doing the remove here. So I'm just remove it and then heapify everything all together. I think this part is a little bit slow, but I think maybe I can find a better way of doing the remove here later on. But for now, I think this should I will just stop here since this is already a kind of long videos. But anyway, I think you guys get the idea here. Basically, the first one is the brute force. Basically, we always do a sort on each of the the sliding window, and the second one is we basically we maintain like two priority queue, one for the left half one array, and the other one for the right half array, and then we just try to maintain that those two the length of the priority queue, and then when we do the medium, we can simply get the first two numbers from those priority queue, and then that's it. Cool guys, I think that's pretty much I want to talk about for this problem. Yeah, I hope you guys like this video. Okay, thank you so much for watching the videos guys, and stay tuned. Bye bye.